Alright, so our warm-up today. Find the volume of the shaded region and rotate about the x-axis. It's a throwback, and one I encourage you to kind of take advantage of. If you struggle like, oh boy, I haven't done this in a while, make sure every now and then, give yourself an hour a week or maybe a little more to go back and look at some of the old ideas. Look through your old exam, old quizzes, just to refresh yourself. It will pay a lot, good dividends, and it comes from final exam prep. A little bit now will save you a lot later. So we're rotating this about the x-axis. I'm going to draw my little mirrored image below. Something looks like this. Maybe picture what a slice looks like if I'm rotating it. I'm going to rotate that outside region like that. That's me rotating it. Then there's also that inside region that gets kind of cut out. Very odd looking shape there. So what is that little slice of the shape? It looks like a washer. It's like a big cylinder with a little cylinder cut out of it. So I can go right to my washer technique. I'm going to kind of break it down to smaller pieces though. For myself, I like to just look at what is the volume of just that slice. It's basically a big cylinder with a little cylinder cut out. So I would have a big cylinder, pi r big radius squared times its thickness. That's a big cylinder. Minus the hole in the middle, which is pi times some little radius squared times some thickness. A little bit of algebra would give us pi times r big squared minus r little squared dx. And if I want to find the total volume, I just add up the volume of all those slices. I add them up continuously from 0 to 4. And I say, what is that big radius? What is that big radius in this case? 4. Is it 4? 2 actually. Right? The big radius squared would be 4. But this is actually, okay, what's the height here? Well, if this is y equals square root of x, and x equals 4 here, square root of 4 would give me this height. So that height would be 2. So big radius squared is 2 squared minus little radius. What's the little radius? Root x, the distance up to the function. And so I have that as my integral. That's the integral that represents the volume. Any question about the setup for that? Yep. Absolutely. In fact, that's the first thing we'll do in the next step. Pi times the integral. Right. Other questions? So I'm really integrating 4 minus, well, the square root of x squared is just x. So if I integrate 4, I would get 4x. If I integrate x, I'll get x squared over 2. I'm evaluating that from 0 to 4. Evaluated at 4, I would get 16 minus 16 divided by 2. Did I mess that up in my notes? I did mess that up in my notes. That would be 8 minus 0 minus 0. So it looks like I get 8 pi. That's that volume. Any questions about this? Alright, so for fun, later go ahead and rotate out the other axis and find the areas and all those other things. You guys can do that later for fun. Some good times, right? Alright, any questions from the warm-up? Once again, just a reminder, look back at those old problems. Don't wait till final exam time to do that big review. Alright. Plan for today. I'm going to start off with questions from the homework or the lab that's due tonight. After that, we're going to do a quick little recap of those first 2 sections of Chapter 9. And I have a bunch of clicker questions that we're going to kind of do along the way just to make sure we're comfortable with those core ideas. After that, we're going to do a little video review and see if we have any questions with the geometric series. Then we're going to go into some example problems and extend those ideas. I want to talk about a difference between the formulas in the book and the formulas in the video. We'll kind of go through that derivation and talk through all that stuff. After that, we'll kind of tease the next couple sections by saying, what happens if it's not geometric? Then how would we find the sum of a series? So I want to start off with questions from the homework and such. But before I go right into questions, I want to answer a question I already received and went through. One of the questions talks about a recursive sequence definition and finding the limit of that. So somewhere in the homework you'll see a question that says, okay, what if I'm dealing with this sequence, for instance, and I'm trying to find the limit of the sequence. So here's my sequence. A1, A2, A3, a dot, 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 out to some AN. Defining recursively, so I have my AN plus 1, I could also kind of find that position as well. Dot, 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 dot. Now I'm going to call this big sequence AK. Now why K's and N's, remember those are just kind of dummy variables, let us associate with the sequence. So in other words, I want to talk about N being this position, some random spot in the middle, and N plus 1, I'm just going to give my larger sequence a different dummy variable. So this is my sequence. The way I define each of these pieces, I could define it recursively using this definition. But now I want to find the limit of the sequence. Does the sequence converge somewhere? And so doing that for recursively defined sequence is pretty different than doing for one with the equation. If we have the equation, we just say, what happens to n as n gets big? But here I don't really have any n's. So how do I work with this one? Okay. Well, the idea is, I'm going to look at the limit of this equation as n gets big. This equation says this side is equal to this side. If that's true always, well then the limit of this side as n goes to infinity should be the limit of this side as n goes to infinity. That should be the same. So what I'm going to do is I'm going to look at the limit as n goes to infinity of basically the whole equation. So on the left-hand side, I would get the limit as n goes to infinity of a to the n plus 1. On the other side, I would get the limit as n goes to infinity of all this stuff. It's like, boy, well, that didn't really help. I mean, the thing I'm trying to find is essentially this. So how do I find out what this is? Well, I'm going to pretend like I know it. I'm going to say, okay, well, let's pretend it has some value. I'm going to call it L. That's what we're trying to figure out. What is L, where L is the limit of the sequence. But if I call it L, well, this side would be L. Now, the limit over here, the limit of a sum is the sum of the limit, so I can really take the limit of the first piece plus the limit of the second piece. What is the limit of 60 as n goes to infinity? Just 60. Then I have the limit of 1/2 times something. That 1/2 can just come out front. So this is really 1/2 times the limit as n goes to infinity of a sub n. But as n goes to infinity, is there any difference between a sub n or a sub n plus 1? Is there any difference between infinity and infinity plus 1, right? I mean, there hasn't been since you've been in grade school, right? We're like, oh, infinity plus 1. There's really no difference. So the idea is it doesn't matter if we're counting from here going to infinity or counting from here to going to infinity, we're going to infinity. So the limit of, as n goes to infinity of this thing is going to be just 1/2 L. And when I think about it that way, I say, great, now I can just solve for L. And that will be the limit. I let L be that limiting value. So now I just subtract 1/2 L to the other side. I get this thing. I multiply by 2, I get this thing. And that is the limit of the sequence. So it's really a different process for recursively defined sequences. You take the limit of the whole equation, and anytime you run into the limit of the sequence, just give it that L value. And then you're all done, solve for L. Questions about that? Okay, let's look at something. Let's see. Let's try this one. an plus 1 equals 2 a sub n. What's the limit as n goes to infinity of that sequence? Write it down, take the limit of the equation, go through the steps, see what you get. Now let's put plus 2 here, just to have some sort of physical value there. How's that look? That looks weird. I don't believe it. I don't believe it at all. If I started at some value, if I let A1 equal 5, for instance, some random number, this wouldn't make any sense at all. Because to get to my next value, I would be doubling this and adding 2. Am I getting bigger or smaller as my sequence goes? Getting bigger. I'm going to double it and add 2, and double it and add 2. But it's going to somehow converge to -2. So the idea here is this is the process when we know our sequence converges. We can use this process. But we have to know it converges first, otherwise it will give us a false answer. Okay? So just be aware of that. That's why we have a lot of tests for convergence, these other things that we'll use paired up with some of these other techniques. So just be aware of that, okay? I won't try to trick you on something for these recursive definitions, but just be aware that there are limitations. Okay. Any questions about this or any of the homework or the lab or anything? Any questions? All right. All right. So, section 9.1 and 9.2. We went through the definitions of everything. What's a sequence? What's a series? We talked about all the representations. So we have to make sure that we're comfortable with all those things. So I have a bunch of little clicker questions. So go ahead and read through these. Write down a value A, B, or C. And then we'll kind of go through them one at a time using our clickers here. Remember, your frequency is DC. I'm going to go ahead and just start the first one running. I'm probably not going to stop and restart every time. You can change your answer any time, so we'll probably just talk through them and kind of change them as we go. So the first one, which of the following is a sequence? How many clickers we got from the audience today? $15, $16. Is that all? Is that all of them? Going once, twice. All right, what do we got here? a little mixed here. Which of the following was a sequence? A and B both look like lists of numbers, but a sequence specifically is infinitely long list of numbers. So it has to be A. Has to be A in this case. Has to be an infinitely long list of number. Now both of these cases I do see a pattern to that number. Do I need there to be a pattern for my sequence? It has to be ordered, an ordered list of numbers, so I have to be able to tell positions, but does there need to be a pattern? Turns out there doesn't need to be a pattern. It's a common misconception. It doesn't have to be a pattern. In fact, I could tell you that I could give you a sequence as the digit place of pi. So the first number in my sequence would be 3, and the next one would be 1, and the next one would be 4. And that's an infinitely long list of values. But there is no pattern to it. It's not predictable. And that would also be considered a sequence. Okay, so this one would be A. What about the next one? Which of the following is an infinite series? So go ahead and just change your values. I'm not sure. I might need to hide that so there's not. Group mentality might just sway it one way or the other here. I'll probably have to do that. Which of the following is an infinite series? Okay, C. Absolutely C here. So the first one is a sequence. The second one is a finite series. And it's actually even written weird. I don't know why there are brackets on either side of it. That doesn't even make sense either. And the last one does look to be a infinite series. All right, so I think I will stop them and start them fresh here. Okay. The next one, the formula an equals sine of n pi over 2 divided by n generates what sequence? So go ahead, write some stuff down on paper if you need to. Check some values here. Everybody see that okay? Lauren, Tyler, you guys can see that all right in the back? Kyle, that's okay? Yeah, projectors. I'm hoping they are warming up, sort of. Yeah, I believe so, right? Yep. You seem pretty mixed pretty early here. Pretty mixed. Let's take a look here. When n is 1, I would get sine of pi over 2. Sine of pi over 2 is 1 over 1. So my first term would be 1. Fortunately, that doesn't eliminate anything. Whatever when n equals 2, well then I would get sine of pi divided by, I don't care. The sine of pi is 0. What about when it's 3? I would get sine of 3 pi over 2. Sine of 3 pi over 2 should give me what value? Negative 1. So I'd have negative 1 over 3. So that'd be a negative 1/3. Now it looks like I have an answer here. 1, 0, negative 1/3. So just an application of plugging in our values to use equations. Yep?
What do they call it when it oscillates back and forth before final convergence? In the case of sine.
I guess I would just have an oscillating sequence. I mean, you could just call it an oscillating sequence, and some converge, some don't. So I don't know if there's a special name for oscillating sequences that converge.
Oh, I thought I understand. It was just like a function that just kind of jumps straight up and then stops at a line, and then when it goes back and forth before final.
Yep. I mean, so we definitely have both cases, right? You can have some limiting value and a sequence just kind of approaching that value, but you certainly can also have a limiting value where you are bouncing back and forth, getting closer and closer to that value. So I'm not sure, I guess, the specific term that they might have used, but you certainly can have that case. Other questions? All right. look at the next one here. We have a recurrence relationship here. So they give us a sub 0 value, the first element here, and we want to find the rest of them. So which sequence are we generating in this one? Go ahead and write stuff out, see if you can identify it, and then choose which one here. Just practicing our sequence representations. Oh, I see a lot of mental math. I have in-laws in the logging industry. Use paper, please. Only got 8. Halfway there. Let's add a new option too. You can always put D if you don't know. I would rather have you put D and not know, and have I know that you don't know, and just kind of guess and maybe get lucky, and then I think everybody knows it. So feel free to put D if you don't know how to approach the problem. Alright, we're at 12, 4 more to go. Yep, right here, there is a comma. This is the first value, and this defines the recursive relationship. Alright, so what do we got here? Pretty split again, pretty split. So let's make sure we have this down. We are starting our sequence with the value of 1. That's what this tells us. A sub 0, your first value here, when n equals 0 apparently, is 1. And then this tells us the relationship to the next one. It says, take the last value, a sub n, square it divided by 2. That's the next value. Then take that value and square it divided by 2. That will be the next value. This is how to get to the next value given the previous value. So if we have our value of 1 and we square it and divide it by 2, what do we get? What's 1 squared divided by 2? 1/2. Alright. And then we take that value. Now we're using the 1/2. We take that 1/2 and we square it and divide it by 2. 1/2 squared is a quarter, divided by 2 is an eighth. That tells us which one we're at now, right? This one, B. Now to find the next one, I would square this and divide it by 2. So I would get 1 over 64 divided by 2, or 1 over 28. Any questions? Alright, let's look at the next one. Suppose you deposit $100 in a bank account. Once per year, the balance is increased by 5% due to interest, and you also deposit $50. The sequence B sub n's that give the balance in the account after n years satisfies the recurrence relation. B sub 0 equals 100, and so they're giving us that first value. And what's the recurrence relationship? How would we define the sequence? So B0 is your first deposit. B1 should be how much money is in there after year 1. B2 would be how much money is there after year 2. Alright, pretty happy with A. It is A. Multiplying by 1.05 is taking your value and adding 5% to it. It's b sub n plus 0.05 b sub n, right? Your value plus 5%, and you're also adding $50. And now notice that this model, it really is built to be defined recursively. Right? It would be much harder to do it in terms of an equation. Of course, you can do it in terms of an equation, but the natural definition tends to be recursive here. All right, so that's that one. One more. Doing our first kind of series definition. So we have it in summation notation, and we want to say, what does it look like if you actually wrote it out? So they're giving you the summation notation version and asking you to do a written out version. I'm seeing some squinting here, so let me just make it a little bigger. Nine, 10, 11, 12, 13. Couple more, 3 more. Alright, pretty happy with B here. What does this mean? Absolutely, we can just kind of test this out. We'll just test some values here. This says write this stuff when n equals 1. Then we'll get 1 minus 3 over 1. Plus, write that stuff when n equals 2. 2, sorry, this is before. 2 minus 4 over 2. Plus all that stuff when n equals 3. 3 minus 4 over 3. 4 minus 4 over 4. So on and so forth. So this looks like 1 minus 3 is a negative 3. Here I would get negative 2 divided by 2, so negative 1. Here I would get negative 1 divided by 3, so this would be negative 1/3. Plus, I believe the next one would be 0, plus dot, 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 dot. So it looks like I have B. And that dot, 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 dot is important because this is an infinite sum here. Alright, so we'll stop that one and go on to the next topic here. So far, the first thing I want to stress here is those last couple were pretty well correlated. Everybody was pretty happy with those. But these first couple were all over the place. So as we go through this stuff, make sure you ask questions because everybody else has the same questions. Right, don't be shy to ask questions as we go through some of these definitions. All right, the next topic we talked about was sequence convergence. We defined sequence, we looked at all the different forms, we defined series, what that stuff was. Then how do we tell if a series converged? We had a fancy limit definition. We learned that our intuition did work. What happens as n gets big? We also had a couple different theorems. We had the bounded monotone sequence. That told us if something converged. So we want to use some of these ideas. So let's look at some more questions here. So I am going to start the next one. It's a little bigger for you guys here. Alright, so this is for the first one. The limit of this sequence, and they defined it for us, 1 minus 1 over n. Does the limit exist? Equal to 1, equal to 2. That's one out of this sequence. The limit of the sequence. I need 5 more. The limit of the sequence, 1 minus 1 over n. Alright, a little split here. Our sequence is 1 minus 1 over n. And we're looking at what happens as n, the limit as n goes to infinity. Well, we can really do this as the limit of a sum. So the limit of the first thing minus the limit of the second thing. The limit of 1 is what? 1. The limit of 1 over n, as n gets big, think about 1 over 10, 1 over 100, 1 over 1,000, 1 over a million. That value is getting smaller and smaller and smaller. So the limit of this thing goes to 0, and we're just left with 1. So this would be b. Any questions about that? Okay, let's look at the next one here. The limit of this sequence. That's 1/10, so the sequence is 1/10 raised to the n power. What happens as n goes to infinity? Alright, that one converges. Excellent. Alright. Look at some of these down here. What about this one? What happens to that sequence? If you don't know right away, do some stuff. Do some algebra on it. Last thing you want to be doing on an exam or a quiz is just staring at it. Lots of different ways you can think about this one. We got 9 so far. I got 12 so far. All right, 14. Pretty strong B. B is the correct answer. 2 ways you can think about this. 1, if I said what's the limit as n goes to infinity of 2 times n to the 4th over 3n to the 4th, just that piece, or we would just cancel those n's and say it's just 2/3. As n goes to infinity, does plus or minus 1 matter? Not really. All right, as we go to infinity, that plus 1 and minus 1 really don't matter at all. So we can really just kind of ignore those pieces and look at the larger limit. Now, of course, we could do this algebraically as well. If we just take that thing in there, and we multiply top and bottom by 1 over n to the 4th, the result would look like this. It would look like 2 plus 1 over n to the 4th divided by 3 minus 1 over n to the 4th. And then we have a limit property that says we can take the limit of the top and the limit of the bottom, and as long as they both exist, as long as the limit of the bottom isn't 0, that will be our limit. So the limit of the top would be 2, the limit of the bottom would be 3, and so the limit of the quotient would be 2/3. All right. All right, let's skip down to number 3 here. Let's do number 3. Number 3 now. And this is really a question of what wins. What's bigger? Exponentials or factorials? So it might be trickier to show so much. This is one you want to just understand. What wins, exponentials or factorials? Absolutely, it'd be C here. Our factorials are going to win. What is n factorial? Well, if I wrote 4 factorial, that is 4 times 3 times 2 times 1. Or 1 times 2 times 3 times 4. So n factorial is 1 times 2 times 3 times 4 times 5, all the way up to n, whatever that n value is. And they grow faster than exponentials, eventually, in the end. That one would be C. All right. All right, I think I'm actually going to stop there. I'd like to get through the rest, but I do want to get on to the lesson for today. I just want to maybe put these up here. You can kind of read through them real quick without answering them, just to get a sense of what other kind of questions we could be asking. Thought about making this like a quiz for today or something, but we should maybe go through some of this together. That way you could also get a sense of kind of the collective understanding as well. Right? The thing I can't stress enough is make sure if you have questions, ask them, because other people have the same questions. Yep.
Rule apply that the exponential is better or more powerful than a power and the factor is more powerful than exponential. Does that only apply when you're taking over for infinity?
Yeah, I mean, you would look at smaller values and say, you know, what's bigger, 10 to the 4th or 4 factorial or something, or and then one that might be the opposite. So this is what happens as n goes to infinity. In the long run, the factorials will always beat out those exponentials. But in the short run, the exponential might be much bigger to start with. Okay? So if you look at, let's see, if we did like, 10 to the n versus n factorial. Well, if I look at n equals 2, I have 100 over here and I only have 2 over here. If I look at 3, I have 1,000 and I only have 6. Right? So the exponentials look like they're much bigger. But eventually, the factorials will pass the exponentials and continue to move away. Other questions? All right, so let's get into the topic for today. Last 2 questions I'll talk about real quick. After we talk about all that sequence convergence stuff, talk about series. What does it mean for a series to converge or not converge? So it was this idea that we're talking about the limit as n goes to infinity of that sum. And that's really how we determine whether a series converge, an infinite series converge or not. We looked at this limit. This is the limit of a sequence of partial sums. So if the sequence of partial sums converges to some number, then we say the series converges and the sum is equal to that number. So for instance, we could have a sequence here. That's a sequence, 2, 4, 6, 8, dot, 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 dot. We could have an associated series. The series would be 2 plus 4 plus 6 plus 8 plus 10 plus dot, 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 dot. Now, this might be kind of a bad example because neither of these things are going to converge. But to find out if this thing converges, I would create a new sequence and then check to see if that sequence converges. I don't go backwards to this sequence, I go forward. This is my new series. To find out if it converges, I look at the sequence of partial sums. I create a new sequence that's 2 and 6 and 12 and 20 and 30 dot, 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 dot. Where I'm saying the sum of the first term, the sum of the first 2 terms, the sum of the first 3 terms. And I'm gathering up that sequence of partial sums. And I'm looking at that sequence. That sequence clearly does not converge here. Therefore, this sum does not exist. Therefore, this series does not converge. And that's the process. Unfortunately, it's not all that useful. Because to really do this, to show that it does converge to something, I would have to be able to write out a formula for this sequence of partial sums. And that's not always easy. But we will start by looking at a few special types of series that do have a nice sequence of partial sums. So we really can talk about their series convergence. So that's where we'll start by looking at some special series. All right, the 2 we're going to talk about are the geometric series and the telescoping series. These are 2 that we're going to look at. So we'll start off with the geometric series. We had a couple big ideas in the video here. When is a series geometric? So the first thing is, given some series, we have to identify that it is a geometric series before we try to find the sum. So first we have to identify it. So a geometric series can be written as the sum from I equals 0 to infinity of a times r to the I. The series is geometric if we have some starting value, and to get to the next value, all we do is multiply by some number. And to get to the next number, we just multiply by that number again. And if we keep multiplying each time by that same factor r, then the series is geometric. Now what we're going to talk about later is how in the video we did one kind of proof to generate some formulas, and the book kind of does a little bit different. And it really all depends on what you call n. There's a little disconnect between the ending power and how many terms there are in the series. So for instance, if I looked at this one here, this is the term when I equals 0. It's the first term, and it's the I equals 0 term. If I look at this one, it's the I equals 1 term, it's the second term. This, of course, is the I equals 2 term, but it's also the third term. So even though the power here is raised to the second power, so I would be 2 in this case, it's the third term. So in the video, when we wrote our formulas, we were just going to sum from I equals 0 to n. And that's fine to do when you get a formula for that, but you have to understand that that n is not the number of terms in the series. Now your book wants you to use n for the number of terms in the series. So if I were to stop maybe at this point, I would be summing from I equals 0 up to 3, like that. But how many terms would there be in that series? 4. Okay. So what your book will do is they'll call this the n minus 1. So they'll sum from I equals 0 up to n minus 1. And that will preserve n as the number of terms in the series. So if you want that, if you want to use, for instance, 4 terms in the series, you would sum from I equals 0 to 4 minus 1, or 3. And that would give you 4 terms in the series. So we'll talk about how that changes the formula a little bit. Right now, that's a geometric series. That's a geometric series. You get them by multiplying by a factor, and you can always rewrite them in this summation notation. So, which ones are geometric, which ones are not? So we'll start a clicker quiz, and we'll look at just the first one. Is it geometric? Is it not geometric? If it's geometric, write it out in summation notation. If it's geometric, write down the expression on a piece of paper in that summation notation, that sum of a times r to that. Number 1, is it geometric? Is 1 geometric? Most people say no. A couple say yes, though. So the idea is if I started at 1, what would I have to multiply by to get to 1/2? Times 1/2. So that would seem to be my constant value, my multiplier. So if I take 1/2 times 1/2, do I get to 1/3? I don't. So it's not geometric. I'm not going from term to term using the same multiplier. So it is not geometric. So we'll stop that one. We will start a new one. What about the next one? Is this one geometric? No problem. So it is geometric. So if it's geometric, write down that summation representation. We'll just stop that right there. So write it in that summation notation. It's the sum from I equals 0 to infinity of a times r to the I. What's a? A is always the first term in a series. Don't overthink it. It's the first term, just grab it. R is the multiplier. What's the multiplier here? 3 halves. Now maybe I didn't see that. Now maybe I just couldn't pick it up. Maybe the multiplier was like 11/7 or something weird and I just couldn't see it. You can always take and divide the second term by the first term, and that will give you the multiplier. So I could always take 6/10 divided by 2/5 to find out what that factor is. All right, dividing by a fraction, the same thing by multiplying by the reciprocal. I would get 30 over 20 or 3 halves. So that will give me the multiplier if I'm struggling to find it. Do that division and it'll work. Okay? And of course, test. 3 halves times 6/10, does that get me here? It sure does. Does it get me here? It sure does. So this is that expression. All right, last one. Geometric or not? Geometric or not geometric? If it's geometric, write out the summation. All right, everybody says yes, absolutely. So the sum is, writing a summation notation, I grab the first term, and my multiplier looks to be a half. So that would be that expression written in geometric terms. All right, so the first step was identifying whether or not it's geometric. The second step is finding the sum. The whole point of recognizing it's geometric is so that we can find the sum. Alright, so to show that we can find the sum, we need to form the sequence of partial sums. Now, the derivation of the formulas is in the book. It's in the video, although once again we'll tweak the n value in here. But it's an important derivation. Right? It's one that you should know. It's one that I would say is quizzable on or testable on as the proof of where these formulas come from, finding this expression. So let's go through the derivation one more time because once again it is important. So our formula is going to look like this. The sum of the first n terms is going to be the sum from I equals 0. So just writing out for this sequence. If I sum the first n terms of this sequence, I will get a minus a times r to the n over 1 minus r. That's the formula. Now we're going to see where it comes from. The idea is I have some sequence and it's geometric. So it looks like this. Dot, 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 plus. And the only difference from what I did in the video was we are going to stop here at n minus 1. Once again, it's a choice of what you want n to represent, that last power or the number of terms in the series. So this should represent, we want to find the sum of the n terms. This is n terms of the series. The idea is I don't know what it is, but I'm going to pretend I do. I'm going to call it Sn here. Let that equal the sum of the first n terms. And so what I'm going to do next, I'm going to take that number, I'm going to multiply it by that factor. And if I do that, well, it's just like multiplying the right-hand side by that factor. So I would get a times my r. That would give me AR. Instead of writing it here, I'm going to write it over here. Just kind of shift it over a little bit. Then I'm going to take a times r times another r. I'll get AR squared. When I multiply this term by r, I'll get ar cubed, so on and so forth. When I take this term, which I didn't write, but you can kind of pretend it's there, when I multiply it by r, I get a times r to the n minus 1. And when I take this term and I multiply it by r, what am I going to get? A times r to the n. When I multiply it by r raised to the first power, I can add their exponents. I get n minus 1 plus 1 times r to the n. So that would be an expression for my sum times r. And all I'm going to do is I have these two equations, I'm just going to subtract them. I have this thing minus this thing. But when I subtract them on the right-hand side, these cancel, these cancel, these cancel, everything cancels, and I'm just left with my first term here, a, minus my last term here that doesn't get canceled. So a times r to the n. And remember, the whole goal here is to find the sum of the first n terms, to find s sub n. And now I'm just going to solve for that number. I have one of them here, I have one of them here. I'm going to factor them out. I'm going to divide by the 1 minus r. And that's my expression. That's an expression, a formula for the sum of the first n terms. So what that is it's really an equation for our sequence of partial sums. And that's the important piece here. It's an equation for our sequence of partial sums. And that's the formula. So now the idea is if I want to find this sum, the sum from I equals 0 to infinity of ar raised to the I power, to do that, I would have to find the sequence of partial sums. Oh, great, I have a formula for it. There it is. There's a sequence of partial sums. Now I have to see if this sequence converges. So I would have to take the limit as n goes to infinity of my sequence. Because I've formed the sequence of partial sums, and I want to see if that sequence converges. So I can do a little bit of algebra on this thing. I'm going to rewrite it as a over 1 minus r minus a over 1 minus r times r to the n. And we see that algebra, I'm just breaking it into two fractions, and I'm kind of writing the r to the n a little over here, so I have this piece. Now, what's the limit? So I have the limit of this difference here. So I can take the limit of each of the pieces. What's the limit of this first piece? What's the limit of a over 1 minus r as n goes to infinity? A minus over 1 minus r. There are no n's here. So the limit of that first piece is just a over 1 minus r. And what about this piece? What's the limit as n goes to infinity of this piece? I have an n over here. I have some number times r raised to the n power. What happens to that as n goes to infinity? Maybe. Could. If I have 2 raised to the n, as n goes to infinity, it goes to infinity. But what if I have 1/2 raised to the n power? As n goes to infinity, what happens there? goes to 0. So the idea is this thing will converge to 0 if r is less than 1. If r is bigger than 1, it goes to infinity, which tells me that this series is divergent. So it converges, and it's equal to this, minus 0, let's drop the 0, it's equal to this if the absolute value of r is strictly less than 1. If, however, it's bigger than 1, then just as we see from this limit expression, that's going to blow up. And then the series will be divergent. So sometimes we can sum this series, sometimes we can't. So these are our two formulas. This is the formula for the first n terms, and this is our formula for the geometric series, the infinite series. All right, so that's basically a recap of the video, except once again, we just switched this was n plus 1 in the video, and this was n. You just kind of shifted it over 1. In that case, n was the last power. In this case, n is the number of terms in the series. So we'll follow this model from the book. That derivation of this formula you are responsible for on a quiz and an exam. And of course, we need to be able to use these two formulas. So any questions about the summary here of these two formulas? Remember, we're able to do this by following that process. We had a series. We want to know if it was convergent or not. We formed the sequence of partial sums, and we looked at whether that sequence converged or not. All right, let's see if you got it. 5 problems. Find the sum if it exists. Some of these are finite, some of these are infinite, some of them are weird, I equals 2 to 5. See what you can do. Feel free to work on these in groups. Feel free to talk to your neighbor. Feel free to raise your hand.
Is there something we can...
Nope, you can keep this in your notes. Alright, so I'm going to start working through a couple of these here. Alright, so we did a bunch of derivation stuff. Problem with doing derivation is it's important to see where this stuff comes from, but sometimes that can make the actual piece you're going to use more confusing. So here's what we need. We need a sum from I equals 0 to n minus 1 of a times r to the I. Anytime we have an expression that looks like that, the sum is equal to a minus a times r to the n over 1 minus r. That's a formula. No limits, no nothing. And we've evaluated the limits in the next piece on the process. So if I sum from I equals 0 to infinity, I have an infinite series. As I said, some mathematicians say, is there any other kind? Debatable. But if you have this series, the solution, no limits once again, is just a over 1 minus r. We've already evaluated the limits to simplify to this. I mean, really, you think about it, we can break this into two pieces. This piece minus some other piece. Well, for summing to infinity, that piece kind of goes away. I mean, if I were to simplify this, it just looks like a over 1 minus r minus a times r to the n over 1 minus r. And we'll kind of see that as we simplify some of these results. But let's look at the first one. A is 3. R is 1/3. How many terms are there in this series? 12. I'm starting at I equals 0 and I'm counting up to I equals 11. That's actually 12 terms. So you can say, okay, how many terms are there? There are 12. So this should be 3 minus 3 times 1/3 to the 12th over 1 minus my r value. Or you can say my formula says n minus 1 is up here. If n minus 1 is equal to 11, What's n? 12. And either way you can think about it, you have to make sure you account for it. Okay, so now let's just simplify this a little bit. In the denominator, I get 1 minus 1/3 is 2/3. Instead of dividing by 2/3, I'm going to multiply by 3/2. Multiply that stuff through, I get 9/2 minus 9/2 times 1/3 to the 12th. And that answer is not 4.5. Right? It's 4.5 minus some really small number. It's 4.5 minus 9/2 times 1/3 to the 12th. This is a very small piece. It makes sense that this should be small. Remember, this is a series. We're adding up pieces, but we know it. If we looked at the infinite series, it would converge to something. So it's like we're adding up more and more pieces, getting closer and closer to some limiting value. So the higher up n values we go, the smaller our steps are as we get closer to this thing. Okay. So the farther out I go, the closer I'm going to be to 4.5. So if you start using n equals 12, 20, 40, anything big, it's going to be hard to distinguish between 4.5 and this little piece that you have to pull off. So be careful. Your calculator is rounding even though it really shouldn't be. If you put in 4.5 on the homework, I'm guessing they'll mark it wrong. I'm guessing they're going to want expressions for things. And if they ask you to do decimal, they should tell you how many places to go. But if they tell you how many places to go, you better make sure you're reading your calculator right. And it's not rounding ahead of time for you. Okay? Questions?
More of a comment.
Mm-hmm.
I rounded off by saying 4.5 because it's converging at 4.5, but the number I actually got was 4.494 decimal.
Yeah, it should. I mean, this. I would guess it's going to be a 4.99999 plus a bunch of stuff, right? It's going to be very close to that 4.5, 4.49999.
So the homework will always tell you how far out the round.
Yeah, so they should tell you something in there about either to keep full precision, or more than likely, they're not going to want a decimal. They're going to want this expression. That's the exact value. Okay. All right, any questions about that? But somewhere in the back of your mind, you should look at that and say, here's my expression, and I got 4.5. That's way too clean, right, to have something raised to the 12th power and all that kind of junk. Okay, so let's go to the next one. The next one is over here. This is an infinite series, I equals 0 to infinity. So I'm going to use my other formula. I'm going to clean up some of my junk here. I'm going to use this formula now. A is 4. I got 1 minus r. R is 1/4. 1 minus 1/4 is 3/4. Instead of dividing by 3/4, I'm going to multiply by 4/3. Result is 16/3. That is the exact value of this infinite sum. Nice and easy, right? I don't have to write out infinitely many terms and do the math. I can, boom, there's my formula. Okay, so let's do that for the next one. A is 2. R is 3/2. 1 minus 3/2 is -1/2. Instead of dividing by -1/2, I'm going to multiply by -2. I get -4. Does that make any sense at all? I'm adding up a whole bunch of positive numbers, and I'm getting -4. Yes?
Can you only use that version of the formula against the value of r is less than 1?
Absolutely. Absolutely. This one I cannot use that formula. 3/2 is bigger than 1. My formula doesn't apply. This thing diverges. Look at some of the terms, right? We'd have 2 plus 2 times 3/2. That's something bigger than 2. My terms are getting bigger and bigger. This is going to blow up. But if you blindly use your formula, you will get some number. But the series does not sum to that number. Right? It can't. It's -4. Right? But pay attention to that, because if you're going too fast in the exam, -4. Right? Please look at that and say, that can't be right. Okay? Yep.
What if it wasn't too better fine? That's the value of r less than 1/4.
Excellent question. Let's look at this one. Right, I equals 0 to 10 of 1/2 times 4/3 to the I. Can't do it, right? 4/3 is bigger than 1. But there's just 11 things here. I can certainly add them up. So it certainly will have some sum. So now we'll use our other formula. This is finite, so I'm going to use this formula. I got 1/2 minus 1/2 times 4/3 to the n. What's n here? 11, right? There are 11 terms, even though I'm summing up to 10. 1 minus 4/3. All right, let's follow this through and do the simplification. 1 minus 4/3 should be a negative 1/3. Instead of dividing by negative 1/3, I'm going to multiply by negative 3. I'll get negative 3/2 plus 3/2 times 4/3 to the 11th. Wait a second, do I have a negative number here? I don't. You might be a little nervous, like I got a negative number here, wherever that was, about here, but it's not, because now, because this factor is bigger than 1, this term is going to be blowing up. It's going to be getting bigger and bigger. So I am taking negative 3/2, but I'm adding a bunch of big stuff to it. So the result will be positive. It is blowing up, but I really don't care. I'm only adding up 11 of them, so I will get whatever this big number is. And it will be some big finite number. So absolutely right. If that factor is bigger than 1, I cannot do the infinite series, but I can always sum the finite series. I don't care if that's a sum from I equals 0 to 2 billion. Right? Just plug it in and get a formula. You'll have something raised to the 2 billionth power. That will be very big. But given enough time on a deserted island with a stick and some sand, I could add those up. Any questions? All right, let's jump to the last one. The last one's also tricky. Our formulas, as we've written them up here, are from I equals 0 to something, not I equals 2. So for me to apply these formulas, I need to start at I equals 0. Now there's two ways I can handle when I don't have I equals 0, because in real life you might not. Two ways I can think about it. Here's one. I'm going to sum from I equals 0 to 5, because that's what I know how to do. But if I do that, I better subtract I equals 0 to 1. And that should work out fine. And now I have two finite zeros or series that both start at I equals 0. I could calculate those out and do the subtraction, no problem. Another way I could do that, and this is the way I actually do it, is I'm going to rewrite that summation to start at 0 and end somewhere else. Okay? Now for me to do that, the easiest way for me to do that is just to start writing out terms. Because if you gave me the series all written out, it would be easy for me to put it back into summation notation. So I'm just going to write out the terms. When I equals 2, I would get this thing squared plus 1/2 1/3 cubed. That's when I equals 3. Get out of here. Get out of here. 4 and 5. And really, I wouldn't have to write all that out even. If I want to write this now as a sum from I equals 0 to something, A is just my first term. I just grab the first term. There's my A. What's my R? Well, I'm still just multiplying by 1/3 to go to the next term. And now I just got to figure out what I'm summing to. I equals 0 up to what? Not up to 5 anymore. What is it? 4, possibly. Let's check it. You always want to check it. If I plugged in I equals 4, the last one, I would get this thing times I 1/3 to the 4th. That's squared to the 4th. If I combine them, I would get 1/3 to the 6th power. I don't want my last one to be 6th. So not to 4, but to what? 3, absolutely. The idea is I want the same number of terms in each case. When I did this one from 0 to 5, I had 6 terms. I'm sorry, I was 2. Here we go. From 2 to 5, I had 2, 3, 4, 5. I have 4 terms. So when I'm done here, I also want to have 4 terms. So I sum from I equals 0 up to 3. And of course, you can also do the 5 minus 2, which should get you to the 3. Yep. As opposed to I equals 2?
Oh, wait.
Because then I'd be actually subtracting that value for 2, but I want that to be included in my sum. Other questions? Okay. Now, applications of geometric series. We're going to do one quick one. I'm going to talk about some other ones you'll probably see in the homework or in the book. One neat thing we can do is we can represent a repeating decimal. All right, so this is something that if you had a finite decimal, you could always just put it over whatever decimal spot you went out to. 777 thousandths. But if it's repeating, how do I turn this back into a fraction? Well, what I can do is view this as 7/10. That would give me this placeholder. Plus 7/100. That would give me this place. Plus 7/1000. That gives me this place. So on and so forth. If I add up all those things, I should get this value. If I add up all infinitely many of them. But this is just the sum from I equals 0 to infinity of my first term, there's my first term, times what? What's my factor in this case? 1/10. So I can represent that repeating decimal as this geometric sum. Great! I have a formula for this geometric sum. To sum infinitely many terms of this, I just take A over 1 minus R. And I can do that because R is less than 1. This looks like 7/10 divided by 9/10, or 7/10 times the reciprocal. And the result is 7/9. Plug in 7/9 in your calculator and see if it'll give you a decimal. It will give you 0.77777. Now there's a lot of other applications to this. Some physics applications, lots of economic implications. I'm going to talk through two, not doing any work, but just stating them essentially. And then we'll leave it at that. This is a classic problem from the other book that students hate. So you guys are lucky you don't have to deal with this one. Is a ball bouncing. If you drop a ball, it won't bounce up to the same height. Right? It will lose some of its energy when it hits the ground. It will bounce up to some fraction of the height. And if it keeps bouncing up to the same percentage, the same fraction of the height, you can represent the total distances traveling using a geometric series. And so in essence, you can find the total distance traveled forever, infinite many bounces, or when the ball stops. So you can add them up using a geometric series. Another neat application is involved with economic stimulus. So the theory in economics is that if I gave you guys $1,000, you would spend that $1,000, or at least a certain percent of it, just say 90% of that $1,000. If you spend that, you put so much money back into circulation, and say, what happens to that money? Well, it also gets spent and moved around the economy. And so you could represent the total distribution of that original $1,000 as it trickles away as a geometric series. And so it's kind of growing as it cycles through. So the impact on the economy can be much larger. So you can look at an infinite series to represent the total benefit from economic stimulus. Now just as a little clarifier there, I'm not necessarily pro or against that stance, so as we're doing the math here. So don't think I'm either positive or negative on economic stimulus. Okay. All right, that's all I got. Next time we're going to open real quickly with telescoping series. We're going to do that real quick, kind of a special case, but I want you to see one example. And after that, we're going to launch into prep for 9.4 and 9.5. There's a bunch of different techniques. I'm not going to have a prep quiz on these topics. Please prepare anyway. All right, these are challenging kind of applications. So we're going to do the integral test, some of the other kind of tests. We're going to do a couple examples of each. All right, that's all I got for you. And office hours are right now. What's that? Yep.
Are you giving your office after 12:30?
Yep, I should be in there later today, yep. I know, just stop this real quick.